Yeah, so good evening, everyone. I welcome to this session on behalf of IMA and Seminar Organizing Committee. Today, we have with us Dr. Ashani Dasgupta. He was BSc student of IMA from 2011 to 2014. Then he moved to University of Wisconsin, Milwaukee, USA, for his MS program. Then recently he completed his PhD degree from the same university. Okay, so I welcome Ashani for this session. Yeah, so you can start.
Thank you, Indra. Thank you for inviting me, and pranam to sir, Swadhin sir. He is here.
Thank you.
We are here because of him, actually. So I'll just start sharing the board. So I hope all of you can see the board. Today we will be talking about something related to boundary of groups. This is a joint work with my doctoral advisor, Professor HRUSKA from University of Wisconsin-Milwaukee. And it actually offers a general solution to a very old problem, like a 30-year-old problem in group theory. And we will understand what that problem is. I know that most of the people here are undergrads. That's what Tatimasi told me. So I tried to design this entire talk in a way so that you can actually take away something from here. Let's see if we can manage that. So we will start with this person. The story begins with Mikhail Gromov writing this wonderful piece called Hyperbolic Groups in 1987. So you can Google Mikhail Gromov. He is one of the stalwarts of this particular field. And in this particular book, let me mark it here. Maybe I can mark it like this, or actually I have a better tool. This one. Okay. So it's like a lightning tool. So this book, it is available freely online. It's very accessible. It's very readable. You can try to check it out. And Gromov started discussions on certain types of groups, which he called hyperbolic groups. Later we call it Gromov hyperbolic group after him. So maybe I should write that. Gromov hyperbolic groups. And in a moment, I'm going to tell you what that means. Okay. What does the word hyperbolic even mean in the context of Gromov hyperbolic groups that Mikhail Gromov is talking about? Because hyperbolicity has a much different meaning in the context of differential geometry, or even in elementary geometry, if you have read about wonderful pieces on hyperbolic geometry. So let's understand what the meaning of hyperbolicity in this particular context is. So to do that, we will try to understand something called thin triangles. Okay, so suppose ABC is a triangle. I write this. So AB is one of the sides, BC is one of the sides, and CA is one of the sides. So here is a definition. We will call the triangle ABC to be thin, or more precisely, delta thin, if something happens. What happens? Well, if you take the delta neighborhood of AB, so you take the delta neighborhood of this particular line segment. How can you take the delta neighborhood of a line segment? Well, you take the delta neighborhood of each point. You take a point on it, you draw a ball of radius delta. You do that for every point, and you take the union of all of those disks or balls. Well, visually it looks like balls. So and then what you get, if you do it for each of these points, you get the delta neighborhood of this entire line segment AB. Entire line segment AB. You do it for every point on AB and take the union of all of those balls. So that's the delta neighborhood of AB. We write it like this. We write the letter delta here and we write AB here to mark how fat this neighborhood is. And then we take another delta neighborhood of AC. So this segment AC is right here. We take the delta neighborhood of this AC and we take the union of both of these delta neighborhoods. So what's happening here? We took two fat regions around two of the sides, AB and AC, and we took the union of them. What we want is, we want the third side BC to be inside this. We want the third side BC to be inside the union of delta neighborhood of AB and delta neighborhood of AC. But here is the tricky part. We want to fix delta. Maybe delta is, I don't know, 2.5 or 0.7 or some number, some positive number. Delta is greater than 0. And we want this same delta to work for all the triangles. So here is the caution. Here is the caution. We want the same delta to work for all triangles. So at the beginning of the game, I tell you delta is equals to 0.7. You draw any triangle on the board, on this special board. Okay, this is a very special board, of course. In general, we will see that the triangles are not actually thin. So you draw any triangle on your special board. You take the delta neighborhood of two of the sides, and the third side will be contained in the union of the delta neighborhoods of the two of the sides. This should happen for every triangle. And you have only one delta to begin with. And you can choose any delta like 0.5, 7 million. Delta can be large. That's fine. But one delta should work for all triangles. Okay. So I'll give you a sort of a counter example. But before I do that, let me tell you what is Gromov hyperbolic. It's very simple. If every triangle is delta thin, then the space is known as Gromov hyperbolic. So if every triangle that you have has this property, this beautiful property, that a delta neighborhood of two of the sides contains the third side. If every triangle in your space has this property, then we call that particular space Gromov hyperbolic. And something that is not Gromov hyperbolic is the Euclidean plane. It is not Gromov hyperbolic. So I'll give you an exercise that you can try. This is very simple. You can do it just using normal high school or middle school geometry. So here is an exercise. Set delta is equals to 5 centimeters. I'll just use some unit here. Doesn't really matter. Let's take delta equals to 5 centimeter. Can you draw a triangle? Draw a triangle such that the 5 neighborhood of two of the sides, union of the 5 neighborhood of the two of the sides, does not contain the third side. Okay, It's very simple. I'll give you a hint, sort of. So you can just use a right triangle for your purpose. Make a large enough right triangle. You have to check what kind of right triangle you will need, such that the hypotenuse of this right triangle is not contained in the 5 neighborhood, union of the 5 neighborhood of the other 2 sides. So maybe the union of the first neighborhood is this one, first triangle is this one, and maybe it's circular, and then the other one is probably this, and a little portion of the third side is left out. So you have to obviously draw that particular triangle that works. There are many triangles that will work. So homework. So we will see, and you can sort of understand this in your mental space, maybe, that the Euclidean plane, in Euclidean plane, you can draw triangles which are like not thin in this particular sense. And we have, on the other hand, surfaces which are thin. So they are known as hyperbolic surfaces. You can think of it as a carpet floating in the air, but the carpet is kind of curved like this. So there is a notion of curvature.
Hyperbolic paraboloid.
Yeah, of course, that's a very nice example. So there is a notion of curvature in differential geometry, but so you will have negative curvature spaces, but I would not go into differential geometry at all, because to understand what we are doing, you don't need to know differential geometry. But if you do know differential geometry, you will get a lot of good examples to think around. So you can Google or read some book maybe on negatively curved surfaces. So a good idea to explore that. So let me back up a little bit. We were talking about hyperbolic groups. We have not yet gone to group part. We have just focusing. We are focusing on the word hyperbolic so far, and we have a precise meaning of what hyperbolic means in our context. It means a space where triangles are thin. That's very simple. The space where triangles are thin. Okay. So one good example of a Gromov hyperbolic space is a tree. What is a tree? Well, a tree is a graph. So it has vertices and edges.
No cycles.
No cycles are there. So you cannot draw something like this. You cannot sort of come back to the same point like this. So there are no cycles. And you can easily check that a tree is in fact a zero hyperbolic space. So delta equal to 0 will work. And I will show it to you right now, why that works. Okay, so let's take a point here. Let's call this point A. Let's take another point here. Let's call that point B. Let's take another point here. Let's call that point C. So I have taken 3 points in my space. What is the space? Well, it is the tree, which contains all these vertices and edges. That's all my space is. So I have taken 3 points in my space, and now I will draw a triangle. Of course, these 3 points define a triangle. I will just mark the 3 sides of the triangle. So AB is one side. You can check this. AB is one side. And then we have, let's draw it in green maybe. AC is in one side. AC like this. So I can probably draw AB a little bit better. Let's make it a little better. So this is AB. Okay, not much better, but the yellowish part is AB. And BC. Okay, so let's try to draw BC then. So BC is this part. So this is AB, this is AC, and this is BC. Okay, so something very nice is happening here. If you just take AB, in fact, we can call this the zero neighborhood of AB. What does that mean? All the points which are 0 centimeter away from the points at AB. Centimeter, just using it like that, but 0 unit away from the points on AB. So that's basically the line segment AB. Union, the 0 neighborhood of AC. So this is the yellow and the green. Notice that that contains BC, because BC is just this, a little bit of red, a little bit of green. So in fact, this will work. If you think a little bit, you can probably write a proof. This will work for any triangle. This will work for any triangle in this particular tree, in any tree. So a tree is a very good example of a zero hyperbolic space. Okay, so far we understand what is the meaning of the word hyperbolic in our context. In the space, triangles are thin. Now let's see what comes next. Why are we interested in spaces where triangles are thin? What in the world are we going to do with that? Okay, let's see.
So excuse me. Hello.
Yeah.
So what does that zero mean in that zero hyperbolic?
Zero means, okay, so if you take a line segment, thank you for the question, please interrupt me. So if I take a line segment AB, if I write N0 AB, what does that mean? Well, we can do it in steps. First, take 1 point P on AB. Now let's write down the set of all points which are 0 units away from P.
That is P itself.
It's only P itself, of course. So it contains P. Okay, let's take another point Q. Let's take all the points which are 0 units away from Q. Well, that's Q. So like this, you take all the points on AB and take all the points which are 0 units away from those points. So you basically get AB back. So the zero neighborhood of AB is basically AB. So this is a fancy way of writing AB. And this is a fancy way of writing AC. And what I am trying to say is AB union AC contains BC. That's why this particular space, the space of the tree, in fact, in this case, the tree is zero hyperbolic. Because every triangle, this delta, you can just have this delta equal to 0. So instead of saying delta hyperbolic, you can say it is zero hyperbolic. Okay. All right. So now that we have this, the question as I posed is that why are we interested in spaces where triangles are thin? What are we going to do with that? Okay. So this will basically bring us to the philosophy of geometric group theory. That's the subject that I work in. So what we are trying to understand here is the algebraic properties of a group. So there is a group given, and if you don't know what is a group, that's fine. I'll come to that in a moment. For the moment, think about it as a set G with some properties. So we want to understand the algebraic properties of a group, but we have a very simple and powerful method of doing that. We want to see the action of the group on some suitable space. We will understand all of these things, don't worry. But for the moment, we will understand it using analogy. We want to understand algebraic properties of the group. To do that, we will understand it using the action of the group on some suitable space. And I will tell you an analogy in a moment. But our hope is that action of the group on that space will give out some nice algebraic properties of the group itself. That's the driving philosophy. And what these hyperbolic spaces, or the spaces where triangles are thin, what they will do is they will give us those spaces on which the groups will act in a nice way. So we built the spaces on which groups will act, and that action will tell us information about the algebra of the groups themselves. That's our entire backstory. Okay, so let's see how we can do that. I'll just give you one analogy. So this is the analogy of a carom board. I like to think about it like this, that this striker of a carom board, you can think of it as group elements. G in capital G, suppose. And these coins here, you can think of this as points in the space. So you can check the strength of each striker by hitting them on the coins. And maybe by looking at the action of the strikers on the points, you can tell something about the strikers themselves. So that's how you can think about one way to think about the basic philosophy of geometry group theory. Okay. So now we come to the second part of the word, group. Okay, so this probably some of you already know. I'll not spend a lot of time on this. So when I say a group G, I'm basically talking about a set G. There is a set capital G with some elements in it, G alpha, G beta, and so on. And there is a binary operation star. There is this closure property. So if you operate any two of these group elements, you will get another element of the same group. And the property operation is associative. There is an identity element E, which if you star with any of the elements, you will get that element back. And there is an inverse element for every element. So for G alpha, there exists an inverse element in the same set, such that G alpha star G alpha inverse gives you the identity element back. So if you don't know group theory, or if you have forgotten group theory, this was a brief primer on that. Having said that, okay, there is Indramani Prasad has raised a hand. Please go ahead. You have something to say, Indramani? I see a raised hand. Okay, maybe not. Okay. So okay, I want to talk about one example because it will be useful for our purpose. This example is like this. It's a very simple example. We take the set as the set of all integers, 1 minus 1, 2 minus 2, and so on. This is the set of integers. This is the set of integers. Okay. So it's easy to see that this set of integers forms a group. The binary operation star is simply addition. And the inverse of 2 is -2. So it is the standard meaning. And the 0 is the identity element. So that's one example of a group that might be interesting for us. We will see that we will be using this example a lot. Okay. Now, one more thing I want to talk about in this context is the notion of a subgroup. So remember, a group is just a set in the first place. So it has some elements, and then comes the binary operations, the identity elements, and so on. So our subgroup is a special subset of G, which is also a group, So for example, if I take from this set G, this group G, if I take 1, 2, 3, this is a subset. But it is not, it doesn't have a group structure. It doesn't contain an identity element. It doesn't contain inverse and so on. But if I take 0, plus minus 2, plus minus 4, and so on, the even numbers, that is a subset of G, but it is also a subgroup of G. So these are the two notions you have to keep in mind, that we have a notion of a group and a notion of a subgroup. Okay, it's fine. So now that we understand this, we also want to quickly talk about something called a generating set. So it's very simple. What you do is, this is the recipe. Okay, you start with a group G. That's your starting point. You have a group G. Now you take any subset, mind you, it's a subset, not necessarily a subgroup, a subset of G. Maybe it contains some elements A1, A2, A5, suppose there are 5 elements maybe in that set. So you take a subset of G, and then you take the intersection of all subgroups of G that contain A. So G may have several subgroups, maybe H1, H2, these are subgroups of G, and you take all the subgroups of G that contain these elements in A, and you take the intersection of all such subgroups. That is also a subgroup of G. Now this is an exercise problem. You can try this. If you take the intersection of all the subgroups of G that contain this set, elements of this set, you get a subgroup of G. This subgroup is written like this, angle bracket A. And it might so happen that this angle bracket A is G itself. That is, all the subgroups that contain those elements are G, the entire group G. I'll give you an example in a moment, you will understand. So then we say A is the generating set of the group G. So let me give you an example. Let's move this out a little bit from my space here. Okay, so okay, now maybe, okay, I'll make some space here maybe. Okay, so here we go. So we had the group G where we have 0, 1, -1, 2, -2, and so on. This was our previous example. Now let's take a subset of G, 2 and 4, these two elements. This is a subset of G. Now we can try to find the intersection of all subgroups that contain A equal to 2, 4. Can anyone quickly tell me what will that be? Can anyone tell me what is the intersection of all subgroups that contain the numbers 2, 4, all subgroups of G that contain the numbers 2, 4? Okay, Pranab Kumar Ponda has raised hand. Go ahead, Pranab.
Maybe 2Z.
Okay, that's so Pranab is saying that this is all even numbers. The group of all even numbers. Angle bracket A is that. That's very much possible. So this is a good example for all of you to think about. So very simple example. You may already have the answer. Pranab may have already given you the answer, but you can think about it. The subgroup, that is the intersection of all subgroups that contain 2 and 4. Is it the group of even numbers? Okay, now let me change that. Take another set B, and let's take 1 and 2 as B. So what is the subgroup or intersection of all subgroups generated by B? Okay, Shubharna Ghosh has raised hand. Go ahead, Shubharna. What do you think?
Maybe the total set G.
So maybe Shubharna is saying this is equal to G, the entirety of G. All the elements of G can be created using these two elements. Okay, so all the, I was not saying it that way. It was all the subgroups that contain 1 and 2, intersection of all of them. Shubharna is saying that it is the entirety of the collection of entirety of G, that is all the integers. So that's another example exercise that you can try. Okay, so as I was saying, that we started with the notion of hyperbolic groups, and we started, well, we first said what is what does it mean to say hyperbolic? Space with thin triangles. Example 3, hyperbolic surfaces. And then we also talked about groups and their generating sets. And we know the basic game that we are playing. We will make these groups act on certain spaces. Act on certain spaces. And by virtue of that action, we want to get some algebraic property of the groups. So maybe the space that we are working with is a graph. Then the graph theoretic properties of that space will tell us something about the group. Maybe it is a topological space. Then the topological property of the space can tell us something about the group itself. Maybe it is a metric space. Maybe the metric properties of the space on which the group is acting will tell us something about the group itself. Of course, we do not know what does it mean by saying acting. I have not made that precise yet, but I had an analogy in that I gave you some time back, and you're probably thinking about something. So I'll make that precise in a moment. So this is the basic game plan, and we will be creating one such space hands-on, a space on which a group acts. Because I'm telling you a lot about groups acting on spaces, so it's better if we give an example right away. So given a group G, let's say 0 plus 1 minus 1 plus 2 minus 2 and so on, and given a generating set of the group, let's say I gave the generating set 1, okay? Given a generating set of the group, in fact, I could probably make it a symmetric generating set 1 and minus 1, let's say, okay? So I take this set A, which you can check as an exercise that it is a generating set of G. So all this intersection of all the subgroups of G containing 1 and minus 1 is G itself. You can check that. Given these two informations, the group and the generating set, we can create something called the Cayley graph of the group. Maybe you know this already, but I'll just say it quickly. It's very simple. A Cayley graph contains two data sets, a set of vertices and a set of edges. A set of vertices and a set of edges. Okay. So what are the vertices? For each element of the group, draw a vertex. So for 0, draw a vertex. For 1, draw a vertex. For -1, draw a vertex. For 2, draw a vertex. For -2, draw a vertex. For 3, draw a vertex. Like this. Okay. I sort of did not draw it like a straight line. Maybe you are having a straight line in your mind, but I did not draw it deliberately. I'm just saying that for each point in the group, you draw a point. You think about it as a vertex. Now you just have to think about what are the edges, because if you tell me the vertices, if you tell me the edges, you are actually telling me the graph. So how do you define the edges? It's again very simple. So what we do is, if G is one of the vertices, that is a member of capital G of the group, then join it with GS, where S is a generator. So take any element of the group, compose it with the generator, and join those two vertices. So let me show it to you. It's quite simple. So if I draw the point 0, that is an element of the group. Now with 0, I can, so this 1 is a generator, -1 is a generator. So from 0, I can compose with 0 one of the generators 1, and I can compose with 0 another generator -1. So composing here means just addition. So 0 plus 1 is 1. So this is 1. And this is 0 minus 1, that is -1. Okay. Similarly, you can go like this. From 1, you can go to 1 plus 1, 2, 2 plus 1, 3, and you will get the desired result. -2, -3, and so on. You get a straight line with dots. It's like a real line you get. Okay. So this is the Cayley graph of G. But mind you, it depends on the generating set. So if I change the generating set, let's say if I have A1, another generating set, which contains 1 and 2, the Cayley graph will look different. So here is an exercise again. Exercise. Draw the Cayley graph where the generating set is 1, 2 of G. Maybe if you want your answers to be checked, you can always send it to my email address. I will respond. Put it in the chat. Okay, you can do it later. Okay, so now we understand what is a Cayley graph. The reason we are studying Cayley graph is because the group is having a left action on the Cayley graph, multiplication by left. So what does that mean? It means that if you have, let me make some space here. If you have G and GS, two vertices of the graph, I'm just looking at one portion of the graph, two vertices and an edge between them, then we can make an action by another group element G1. And this is like this. You multiply G with G1 to the left. You multiply GS by G1 to the left. So G goes to G1, G, GS goes to G1 GS. So this vertex goes to this vertex. This vertex goes to this vertex. Now question is, what happens to this edge? Does it go to the edge connecting them? Is there an edge connecting them? Of course there is, because G1G is one vertex, and the rule that we defined is that you just multiply with that number or that group element, a generating element, to get the another vertex to which it is connected. So certainly this edge goes to this edge. So now it becomes a little bit clear that what is it I mean by the action of the group on a space. This is an example, but I will make it a little bit more precise. So here is precisely what's happening. It's a definition. Suppose gamma is a graph. Graph means it contains vertices and edges. Maybe it is a Cayley graph. Then there are graph automorphisms, graph maps from gamma to gamma. So there are many such maps, phi1, phi2, several maps from gamma to gamma. They are mapping vertices of gamma to vertices of gamma, vertices to vertices, edges to edges. Compatibly. So basically, if A and B are two vertices, if A is mapped to C, B is mapped to D, then AB is mapped to the edge connecting C and D. So the edges are mapped compatibly. Okay. All right. So vertices to vertices, edges to edges. Now that we have this, what we want to do is we want to think about these maps as the element of the group that we are studying. So if G is a group, this is the group we want to study, then capital F is a group homomorphism from G to this set of automorphisms. If this is too hard for you, think about it like this, that each element of the group is mapped compatibly to some map from gamma to gamma. So you can basically think about group elements as maps of that particular space to itself. Maps of that particular space to itself. So you have this group G, which contains a bunch of elements. You have this graph gamma, which has several points and vertices and edges maybe. So maybe it's like this. So what you are doing is you are thinking about each of these group elements as maps from gamma to gamma. Of course, I have to say a little bit more. I have to say these maps are compatible. I have to say this capital F map is a homomorphism and so on. But let's not go into the details. So I gave you an example of a graph, that is the Cayley graph. And I gave you an example how a group can act on its Cayley graph, left action. This brings us to the meat of the matter. You see, in the last few minutes, I will briefly describe the main work that we did. We had a group G. We could have worked with a Cayley graph gamma on which the group acts. But to extract more information, we created a space M. We created a space M on which G acts suitably. Why did we do that? Well, we hoped to extract algebraic information about this group by the virtue of this action. Now, how did we create this space M? What was the method? It's very simple. We call this space M the boundary of the group. The space M as the boundary of the group. Now, there are certain graphs called fine hyperbolic graphs. So just for the sake of it, I will draw a picture of a graph. It's not a tree. There are a bunch of edges and vertices. It's probably an infinite graph. Let's call this graph K. Let's call the name of this graph K. And we already know by some method that G has an action on K. Hyperbolic means the triangles that we can draw on this graph are thin triangles. We talked about thin triangles. I'll not talk about a fineness of a graph. It's very simple, but it will take more time. It will not do any justice to the time that is left. So we know that there is an action of this group on this graph K. Now, using that, we can define this space M, the topological space. And this is very nice. You can sort of imagine what's going on. And I will show you exactly how we are constructing this thing. Take any point A on this graph. Take any point A on this graph. And from that point, draw infinite rays that is coming out of this point. All roads that goes out for infinity, toward infinity in some sense. So I'll write that. Take all the rays emanating from A, this particular point A. All the rays coming out from A. In some sense, this boundary M is this particular set. There is something else you have to do. There is a quotienting that you have to do. But broadly speaking, this is what's happening. And this is very, very, very much easy to understand if you have an imaginative mind. If you take any point in the space, how do you think about the boundary of the space? Well, one way to do it is think about all the roads coming out of that point and leading off to infinity. That road is sort of hitting infinity, the boundary, at some point. So this is a different way of thinking about boundary. Take a point on your space and then think about a ray coming out of that point and take the collection of all of those rays, and then you have something called the boundary space. It's a topological space. It's a topological space, if you know what that means. If you don't, that's fine. It's very simple. You can just look up the definitions. But turns out that the group not only acts on K, that is this graph, the group also acts on M, the boundary of itself. And if we can tell something about the topology of the boundary, then we can say powerful stuff about the group itself. So now we come to the last part. If G, well, I did not explain what would relatively hyperbolic mean. I just said what is hyperbolic in some sense. But if GP is relatively hyperbolic and if the boundary is connected, so you already know what that means. If G is acting on a fine hyperbolic graph K, and if you take any point on K and take the collection of rays coming out of that point, those points, those rays, you have to think of those each ray as a point. Those collection of rays is the boundary, and if that boundary is connected, we showed that it is also locally connected. Now, this problem has been tried for at least 2.5 decades, if not more, and there were partial solutions available due to Bryant Bowditch, due to Tukia, and Swenson and other researchers in this field. We could solve it in its full generality. It's a very recent result. We are still cleaning up the last portion of our draft too, so we hoped we solved it. We will be. It's up for submission now, but it's very nice actually that if it is locally connected, it has far-reaching consequences on the properties, algebraic property of the group itself. So with that, I'll stop out here. If you have any questions, I'll be happy to answer them. I've also put my email address in the chat. If you need, if you can also email me. Yes, Shashwato Guho. Go ahead, Shashwato.
Yes, sir. Sir, boundary of a group is always a topological space.
Yeah, you can actually put a topology. So it's a set. Let's think about it first. You take all the rays and you are thinking about each ray as a point. Well, that's definitely a set. Now, on that set, you can put an appropriate topology that gives out nice properties of the group itself. So yes, you can put a topology. Of course, you cannot do this with every group. You can do this with relatively hyperbolic group. And in a sense, relatively hyperbolic group, I sort of hid the definition of a relatively hyperbolic group in this line, where I said that G is acting on a fine hyperbolic graph in a certain way. That is sort of the definition of a relatively hyperbolic group. If you can find such a graph on which the group is acting in a certain way, then we say that group is relatively hyperbolic. So now that you have the graph, you can obviously construct the boundary and say that the boundary is, and put a topology on it and study its topology.
Okay, yes. Okay. Thank you, sir.
Good question. Any other questions? Anyone? Jatin Sharma, please go ahead.
Yes, sir. Can you recommend any good book for beginners for hyperbolic geometry or topics related to this?
Yeah, actually I can. Yeah, there is a very nice book called, that's a very good question actually. Thank you for that. This is by Bonahan. It's a very nice book called Low Dimensional Geometry. I'll just type it in, okay? Hyperbolic geometry is itself very fascinating, but note that what I just did, it's Gromov hyperbolicity, but I think it's a good place to start. Like the differential geometry angle is a very nice place to start, and I put the name of the book in the chat. It's a very nice book, but there is another book which is even, I think, more, it's like written by a master. It's called Geometry and Imagination. This one is by Hilbert. So Hilbert hints at some of hyperbolic tools, I think, but the other book's author name is Francis Bonahan. I'll type it in again. This is the previous one. Francis Bonahan is author of the previous book, the first title that I gave you. Good question. Excellent. Anyone else has a question on anything? If not, I will ask. I'll thank Dr. Patnaik. So whatever we are today because of him. Thank you, sir, for teaching us and letting us into this wonderful world of mathematics. And thanks, Indra was my colleague in in IMA. So we had very nice memories. Thank you, Indra, for inviting me.
Yeah, so let us thank Dr. Ashwini for his nice talk about geometric group theory. Yeah, so thank you, Ashwini. One second.
So
Yeah,
I have two more announcements for the people who are attending this seminar. So next week we have a seminar on career perspective for undergraduate and postgraduate students. So those who are out from outside AMA, so I invite you all to attend the same in the next Friday at same time. Okay, this one is the first announcement, and the next one is about we have an advertise. We have the admission notice of IMA. Those who have interested for doing a masters in mathematics with data science or computational finance, they can see our website, and also they can recommend or they can tell if somebody who is passing from +2, they can also go for our BSc in mathematics and computer science. Okay, these are the announcements. So we will meet again on next Friday at same. Thanks, sir. Okay, thanks, Ashani, for the nice talk.
Thank you. Okay, bye.
Thank you.